few things to tell you. The first is nothing we do today will be on the exam. I mean, take your notes, but there may be a homework assignment which won't be due till at least Thursday after the exam. So you don't have to worry. Pay attention. You don't have to worry about this stuff for the exam. For the exam, you can bring a calculator. I'll bring my box of calculators. There's no guarantee you'll have one. If 2 people need them, we'll try and work it out. Oh, yes?
Yeah, like it's not on the exam, but it's on the next exam, or it's
Yes.
on the...
Yes,
Oh.
yes. You don't just throw your notes out the window. Yes. It will be on a future exam. Yes. It's still important math. If you're allowed a sheet of notes, no size limitation. I've never had someone come in with a magnifying glass, but to read their notes. But 2 sides, 1 sheet of paper, whatever you want to write on it. Put a prayer, you know, that helps. Okay. We're going to go over a couple of problems, homework problems in a minute. I want to kind of back off and, I know most of you are just a semester away from your previous educational experience. And what I'm going to say may not apply to you. If you've done well in math, it probably doesn't apply to you. If you've struggled, maybe you know what I'm going to say, but it's always worth, wasting a little time here on this. Somebody will get something. The bane of all students who struggle in math is the math exam. Oh, there's the math exam. And you get nervous. Tense, you see a problem, you don't know how to do it. Maybe you could do it, but your mind goes blank. So I'm going to give you some basic test taking advice. I usually give this to students who are like doing SATs, but there are a few things you should do with the math exam, unless you know that you're a whiz, you can just go right through it, no problem. You've done this before. First thing to do is when you get the exam, you want to kind of leaf through it, like what's involved. Now this is a lot of pages. I also want to say I told someone wrong a couple of classes ago. They asked how many problems. There's actually going to be 25 problems. However, a lot of them are really easy. Not all of them. And therein lies my next point, which is if you're a little tense about the exam, you're not sure you're going to ace it, it's a good idea to triage. By that I mean, you first want to take a look, what does it look like? How many pages? What are the problems? Just briefly. And then, starting at the beginning, go through and pick out things you just know. I know how to do that. I know how to do that. Do it. Just go through like that. If you don't, or you're not sure, it's going to take a while, skip it. That way, you're going to get through the whole exam pretty quick. It won't be done. But you'll at least have some momentum. Your mind will no longer be like worrying about, oh, I don't do well in math, or whatever demons you have. And then you can go back and then you can kind of think out. Say, well, of the ones that are left, which is the easiest for me, right? Do that one. And go through that way. That way, the hardest problems, the one that you want to have the most time for, it'll be at the end. You'll know how much time you have. You'll know you have plenty of time. You sit there and you stare at it, and maybe you don't know how to do it, something will come to you. But, okay, so that's kind of item number 2. Having said that, I mean, these are general statements about math. Is that you will not have time pressure on this exam, except that you put on yourself. Everybody will be done by the end, right? If at the end you feel like you need more time, really, just let me know. Go down to my office and finish it. Something else I was going to say. Yeah. I don't think you'll have this problem with my class, but every once in a while, you're taking a math exam and you're sitting there and you start working yourself into a knot, and then you just can't think about it. It's like I know how to, you just can't focus. The best thing you can do when this happens, if this ever happens to you, is to stop. Just stop. Say, all right, stop. You put your head down on the desk. Take some deep breaths. Close your eyes. Relax. Take a minute, 2 minutes, take 5 minutes. Because you're going to do so much better if you just stop, relax, get out of that fluster you put yourself into. Now, one of the harder things is if you're in that state to know, just stop. You can only learn this by experience. And actually what I said about there being 25 problems, even that isn't quite true. There's 26, but the 26 is extra credit, so you don't have to do that. Still get it for. All right. Before I go on, any questions? I'm just going to repeat this because some people came in late. You can bring a calculator. You can bring a sheet, one sheet of paper, double-sided. Write whatever notes you want. Anything you feel like. Write the quadratic form you want on there. You need that. Anything you want, you can put on there. Okay. Any questions about the exam before we move on? I'm getting cold and I'm sweating. All right. So, what are the instructions for 72?
72 is finding the x and the y.
Finding the x
They
and
want me to
y
find the x and y
intercepts?
Yeah.
Really? Okay. Well. Okay. I misinterpreted. All right. So, what are the x and y intercepts? They're the place where the curve is going to cross the x to y axis. When it crosses the x-axis, y is going to be equal to 0. When it crosses the y-axis, x is going to be equal to 0. So let's see if we can just use that. So if y is 0, we have x squared minus, oh, that's 0, that's 0. 1. So that could be plus or minus 1. Did I do that right?
Yes.
Okay. The y-intercept is where x is 0. So let's look at that. 0 minus that's 0 plus 3y equals 1. Those don't matter. Y equals 1/3. So, about there. Now, this is kind of an interesting looking animal, isn't it? I mean, it's x squared minus y, x plus 3 equals 1. So I can solve for y. We get y plus 3 equals 1 minus x squared. I'm going to switch these. I'm going to make this plus and switch x squared minus 1 over x plus 3. And I don't know, since I have it all set up here, I'm just going to quickly take a look. So we've got x squared minus 1. Is this plain yet? No, it's forming up. Divided by x plus 3. I made a mistake somewhere here. Either in my graph, either in. Huh. Let's try that again. Squared minus. Oh, that's where I made a mistake. X minus 3. Yeah, I think x minus 3. You don't have to do any of this. There we go. All right, so there's our -1, 1, and our 1/3. We can even, I'm showing you this because when you're doing homework, you just want to get it done and you think you did it right, fine. But if you want to kind of explore it a little, Cosmos is nice here. Oh, look at that. It's telling me that that point was 1/3. All right. So, how much fun? Is this the same question?
No, that one is trying or testing the
I'm sorry.
testing the
Oh, look at the symmetry of this. Okay. So what kind of symmetry are we looking at? We're looking at x minus x, y minus y, or xy minus x minus y. In other words, we want to see if we make x, we switch it, we're going to talk about this later, reflecting. We reflect it across the y-axis. We have the same curve or not? So, right, say, we substitute minus x here. Well, I can do a little work on this, but I think you can kind of see already what's happening. It's not going to work, right? So it's not going to have this kind of symmetry. Put an X here. No. Well, looking ahead, I can do the same thing with y, and it's going to turn out the same way, right? I can do that if you want. But, all right, so we've got one other possibility. We're going to switch both x and y. This is symmetry across the origin. Negative x. We're checking for it. We don't know that. And here, x squared, y squared, plus xy equals 1, which is the same equation. So yeah, it has this kind of symmetry. I forget, does the book give a specific name to that type of symmetry? And I call that an odd function.
No, so when they're like testing for symmetry, they just kind of have you test for symmetry period. I don't even think they give you like different.
I just was wondering, as a name. they
With
give-
respect to the origin?
Yeah, okay. They didn't give it any special emphasis with respect to the origin. Okay, any other homework problems?
45.
Please. I'll erase you draw.
Oh, I don't remember that. Is he on the picture?
Don't you have the online thing?
Oh.
Here it is.
Somebody? 45?
Has symmetry.
Oh!
I don't think it's like an official.
5, negative 5. Another one?
Or 1.
Okay.
Yes, it's like a point on the y-axis.
Oh, on the y-axis. So, before we do our algebra, let's at least, picture is worth 1,000 words. So you got 1, negative 1. Got a point here. And we've got a point 1, 5. Oh, negative 5. The one's on her. All right. Something down here. 1, 1. Wait, I'm sorry. 1, 1. All right. Sorry. 1, 1. And none of this really matters. And we want to find a point that's on what axis? It's on the y-axis, so that tells me, right? And we want to know where this is so that it's equidistant from each of these. Okay? That's the step. So now, I don't think I have to say this at this point, but if you're doing the homework problem and you kind of like, couldn't even finish my thought, you draw a blank, but you think, well, what's in this chapter? Let me go look at the chapter, see if there's anything there. Okay.
It's finding the y-intercept, not the
Yeah.
Well, finding the y-intercept. So where x is 0. You got that right? Is that what you were going to say?
Yeah.
Okay. Thank you for not making me use the wrong way and having. All right, so what are we going to use here? What have we learned in the chapter that's going to tell us about the distance between points?
distance formula.
The distance formula, yeah. So the distance formula, let's look at 5, negative 5, and 0, y. And what's that distance? It would be the square root of 5 minus 0 squared plus negative 5 minus y squared. And now we have same thing with 1, 1, right? Square root of 1 minus 0 squared plus 1 minus y squared. These are equal, right? That's what we want. So now now it's simple, right? We just have to find y. Well, first thing you should do is square both sides, right? There's that problem. And this is 25. I can always multiply what's in here by minus 1, because when I square it, it's not going to matter. So what do I get? Y squared plus 10y plus 25. No. The a plus b squared, if you know that cold, it's easy, equals 1 plus, all right, y squared 2y plus 1, that's a minus b. Really? It's going to cancel. That makes life much easier. Bring 2y over, I get 12y on this side. 25 plus 25 is 50. I'm going to subtract that from 2 minus 48. That equals minus 4. So that's telling me that the point 0 minus 4 okay, now, here's a nice thing about having drawn a little picture is I can look right away and say, that's not plausible. And I look at that and go, yeah, that looks completely plausible. I might have made an algebra mistake here, and maybe I want to plug this back in to my original 25 minus 41 1 plus. That's what I was going to come out. I think I got the answer right. What's wrong with my check here? Oh, wait a minute. This is 0. You get old and your brain scatters, especially when you're in front of a blackboard. I'm going to leave that to you to check my work. I made a mistake going. Oh, you think I got it right?
Yeah, I got that.
Like 3 negative 2.
Well, it has to be 0, right? 3 negative 2 might be equidistant, but it's not on the y-axis. Did you come up with that in an interesting way? Even if it's not what the question is? Oh, all right. I mean, we could you could do something like this. We could say xy, right, and xy, and then we get an equation in xy. Instead of just being a point, it would be a curve, or maybe it's a line. It would be a line like that. Points equidistant, yeah. Perpendicular bisector. All right, any questions about this? Any other questions? So, where we left off, we're working our way through section 2-2, which talks about graphs of functions. And we're going to talk about something I suspect some of you have heard of called the vertical line test. Anyone heard of this? Okay. Pumping heads, that's good enough. So what the vertical line test is for is, if you see a graph, is it represented by a function? Now, the graph is just a bunch of xy points. And a function is a map, from the x to the y points. So the only thing you really have to worry about is whether you have two x's, or whether you have an x which goes to two y's. Because that would not be a function, right? That's the rule. So there we have the vertical line test. You kind of mentally look at the graph, and have to draw kind of an infinite number of lines to be sure. But do any of these vertical lines go through the graph more than once? If they do, it's not a function. Now this is f of x equals x squared, which is a function. If I find the inverse of this, we're going to talk about inverses later in the class. Well, the inverse relation is plus or minus the square root of x, which is not a function. We can make it a function by just saying our original function is only x greater than or equal to 0, and we get rid of the minus here, and it becomes a function. Vertical line test. All right, let's look at a different graph. This is the graph of x squared plus y squared equals 1. This will become very important later in the class when we study trigonometry. And this is just the graph of a circle. And we ask ourselves, can this represent a function? We go, oh, wait a minute. It's nothing but lines that pass through 2 points. So this is not a function. All right, that's all there is to it. Questions?
So the diagram so you provide is just showing if it's a function or not.
The vertical line test allows you to look at a graph of some equation or something and determine whether it could be a function or not, or it can eliminate that possibility. That's what it's for. It's unfortunate that the progression of mathematics is such that I can't talk yet about the horizontal line test. There is a horizontal line test. We'll get to that. It's not the same thing. Okay. We're not really changing gears much here. We're going on to section 2.3, which is about abbreviate information you can get from a function. Oh, from a graph. From a graph of a function. So, having learned from this example that a circle is not a function, I'm instead just going to graph a circle. Does this pass the vertical line test? Yeah. This is a function. So what can we learn from this? Well, the first thing is, you'll notice that on the x-axis here, we have, this is the same as I have over there, except it's going to be y equals square root of 1 minus x. This is just the upper half of the circle. X can have these values. It can't have a value over here. You can see that right away. X is greater than 1. This is negative, and it's an imaginary number. So we're dealing with real numbers. So this is what we call the domain. Talk about the domain of a function. Just the function, the values you put into the function, or you can put into the function. The next thing we can get from this graph is we can look at the y values. And that, of course, has a name called range. So for this function here, we know the domain can be what? X, such that, well, start with -4. That's just what my notes say, but I'm not calling my notes. I could write this as x is between -1 and 1. Or I could say the absolute value of x is less than 1. That would be the same thing, right? And range, y is what? Y is, I don't want to write it this way. I'm just going to write just the interval from 0 to 1. There's a number I can plug into this, or I can get any number between 0 and 1. Yeah, I notice I have a bigger circle. Yes?
When you're writing domain and range, can you always write it the way you wrote range on problems? Or do you have to write
For
it
me,
for you?
for me, you can write it however.
Oh,
Yeah.
however you want.
Unless I say, write it this way,
Okay.
or write it that way. Or write it both ways, as I might on the exam, just to see if you know how to do it both ways. These things slip out somehow. All right. All right. So, information you can glean from looking at a graph. You can see whether it's a function, maybe figure out its domain and its range. The next section of the book, I have a little caveat here. They're going to talk about solving a problem graphically. Now, here's my opinion on this. It's often nice to draw a picture so you can get a feel for what's going on. But in the real world, you know, unless, I guess I could see if you're doing some kind of, when you're studying something from, I don't know, astronomy and you have some kind of data, and some kind of line going through it, and maybe you need the intercept, you might use a graph. But you can do this algebraically too. In general, you're going to use algebra, not paper and pencil, or even, as we're going to do in a minute, Desmos. So, again, I think it's a good idea to draw a picture so you understand the problem. So we're going to look at 2x squared plus 3 equals 5x plus 6. This is an off the contorted problem I came up with. Given my druthers, I just put it on one side of the equation. I have a parabola, and I look for the roots where it goes through the x-axis. But the book thinks this is worthy of solving graphically, so go ahead and give it a try. So first equation, you can do this on graph paper. You can start a fire by rubbing 2 sticks together, and it still works. It's just not a very modern way to do it. communicate with someone by beating on drums, you know, but we have cell phones, yes.
Is 2.3 gonna be on the exam next week? Or
Did you come in late? Oh. Nothing today will be on the exam. Okay? All right. It'll be on the next exam. Okay, so this is parabola. And what's the other? 5x plus 6. Maybe that wasn't a good idea. So, all right. Got a parabola, I've got a line where they intersect. I mean, those points are on both curves, so they'll solve the algebraic equation. So we can go over here. Yeah, I think negative 0.5 and 3.5. And then up here we have 3 and 21. So, under some circumstances, this might be a viable way. Alternatives are, I guess I'll just put this away. We could try and solve this directly. Now, maybe it's not a nice equation. You know, maybe this is,
Make it look really awesome.
right? Maybe it's some crazy equation. And we can't solve this exactly, but we have a little TI computer or Desmos, and you look, you have, you know, come during the break. There's a function here called calc, and they have a function called intersect. And we'll just numerically approximate the answer. It might get an exact answer, might get the exact answer. If it's a square root, it obviously can't. Just regular numbers. So, all right, so that's solving equations graphically. Okay. All right. So clean this up. Now, at this point, we're going to introduce something new about functions, which you can get from a graph also. Out of a specific context, this may seem a little, why are we learning this? This is going to be an important idea, which is the idea of increasing function, decreasing function, or increasing or decreasing function on an interval. We're going to learn a little bit about it. You can take the next class, calculus. We're going to learn a lot about it. So first we need a definition. I'm going to write a very mathematical definition, and then we'll go over how it works. Okay, so an increasing function f of x is an increasing function. If for all A and B, you could also write this upside down, A for all A and B. Members of the domain of the function. A less than B implies f of A is less than f of B. Okay, let's try and think about that for a second. We have some function, which I'm going to describe with a graph. From left to right is increasing for every A and B. If A is less than B, then f of A is going to be less than f of B. Now, I thought it very simple, just a line. It doesn't have to be a line. It can be as long as every point along the way is going up, that's an increasing function. So that's our definition. That's kind of how it works. The nice thing about a definition about this is a little very specific and very mathematical. But when you're examining a function, if you can show this, that for every A and B, A less than B, that f of A has to be less than f of B, you know it's increasing. Right? No, this kind of weird stuff occurs to anybody else, but 90% of the people in the world are right-handed. We read from left to right. If it was the opposite, we'd probably be using the opposite definition. Right? We'd probably think increasing is going that way. But those decreasing function definition looks almost the same for all A and B, members of the domain of F. I'm abbreviating here. A less than B implies f of A greater than f of B. Well, if you understand this, you just have to reverse your thinking to see that if instead of going up, line is heading down, that my f of A here is going to be greater than my f of B. So that's a decreasing function. Now, this same idea, we can extend it. We might have a function that's neither increasing or decreasing, but it might be increasing or decreasing on an interval, which we'll call for the moment I, something like this or this. So the definition for increasing on an interval, interval I is, it's going to look the same for all A and B, members of I. A less than B implies f of A less than f of B. And you can kind of fill in the decreasing on an interval would be the same except f would be greater than f of B. So let's look at an example here. Example from the book. I wonder if I can, I can make this a little better. I want to stretch this out so it looks nicer, but I don't know how to do that. I know I've done it in the past, though. You don't see it.
It's on the y-axis, I think. If you lower the numbers, I think it'll.
Oh, that's a good idea. Oh, well, that didn't work. But you've got the right idea. It's the x-axis. Maybe you said x, I didn't hear you. There we go. Okay, now it makes sense. All right, so, let's take a look at this. Where is this function increasing? Well, it looks like from here on down, here over to about 1, it's increasing. I guess, under the board here. So from negative infinity to 1, it's increasing. You can just see that from the graph. And then from 1 to 0, it's decreasing.
Parentheses for decreasing, parentheses for.
We're going to talk about that. From 0 to 2, it's increasing again. And from 2 on to infinity, it's decreasing. Okay, so I understand your point. You're thinking, well, can 0, is it both increasing and decreasing? Well, it's part of the interval, right? If I said, wait a minute, negative 1, isn't it? Sorry. If I said like negative half and 0, they fit the definition, right? It doesn't have to, no, 0 can be in both of these intervals. We always write, whenever we're talking about an interval that goes to infinity, we always call that an open interval, because you don't get there.
Do you ever use a closed interval when you're talking about something in the middle though? Like is there an example in the equation that would have like curved brackets but not be infinity for like, this kind of function?
Oh, yeah, oh, yeah. Let's do that. And then we'll get to it, right? If I said, trying to phrase this right, because I keep coming up with a closed interval. I have some function, and, oh, 1 minus 1 over x So what's the domain of that function? Oh, I didn't get that. Yeah. No, just like that. What's the domain of that function? Well, it's really, you could just say x not equals to 0, but you could say infinity 0 union 0 to infinity. I mean, does that fit what you were asking about? You wanted to know about it. Would you ever need an open interval to describe something? Or do you
Yeah.
mean?
Or like, I meant like in the case of like the one, like an increasing, decreasing interval function.
Oh.
But that was just like out of curiosity.
That's a good.
Or do you only ever use like
Yeah,
for
it's
brackets?
a good question. I have to think about that. What you're saying is, I have some function. Oh yeah, I got a function for you. Okay, just have to make it up. Let's try x squared plus 1 over minus x. So where is this increasing? I'm sorry. Away from your break. I think this will do it. So where is this decreasing? Oh, I have to wait for it to turn on. There it goes. Where is it decreasing? Anyone see that? One over here, it's going off to infinity. Oh no, actually about 2.5. I'm just guessing where that point is. But 0 is not included, right? It's not defined as 0. So that would be an example where you have a function which is decreasing on a half open interval, I guess.
Yeah.
Yeah, and we could make this piece go up, and it would just be a. How can we do that? Oh, we have a function. Oh, we're not gonna get there for a while. Later in the class, we're going to study a function called the tangent of x. And it kind of looks like this, and it looks like this, and it goes from pi over 2 to pi over 2. And this question will come up. You don't even know this now. You probably don't even need to know this for the second midterm. But the domain of this function is going to be negative pi over 2 to pi over 2. And these are open intervals because it was asymptotic. We'll talk about this. All right, why don't we take a break? Take 5 minutes. Check your email. Get a drink of water.
Yeah.
I don't know. I still have to check in.
What number is it?
I'm so I think I can check in, but like, I don't know. You think I know the number like that? I'm so scared to take that suitcase off to
I'm going to switch gears for a second. We're going to student ask about a problem. We want to find the solutions to this by completing the square. Now, I'm going to remind you that you teach you this technique because there are circumstances where you need to complete the square, but you won't be able to use the quadratic formula. So how does this go? Assuming that A is 1, makes it nice and easy. If A isn't 1, then just divide by whatever A is, right? And it'll be 1. We take a look at B here, right? A, B, and C, which is negative 4. We divide it by 2, we square it. So what do we get here? We get negative 2 squared is 4, right? Yeah. This is the way I like to do it because then I don't make a mistake. So to complete the square, you need 4. You have to add it to both sides. And now this becomes a perfect square. So this becomes x minus 2 squared. That's a minus b squared. That's the pattern. I want to subtract 2 from both sides to put it over here, equals 2. And now I just go through this regular process to solve this. I'm going to find the square root of both sides, but that's going to end up giving me 2 values here, plus or minus the square root of 2. This becomes x minus 2 equals plus or minus the square root of 2. And from there I can see that my solution is x is 2 plus or minus the square root of 2. So those are my 2 solutions. Now if we go ahead and do this with the quadratic formula, you'll see you get exactly the same thing. And if you try to factor the original, you'll find you can't do it. Which is not a surprise when you end up with a radical in the solution. All right, that's good. All right. Now we have to switch back. So we were talking about increasing and decreasing intervals. So, what about that that graph? And we had an interval, well, we went out to infinity. It was increasing, and we had an interval that was decreasing, and we had another interval which was increasing, and we go up to infinity and decrease. Right. So, what about these points where this thing changes? It appears that from this point, if you go in either direction, it's going down. This is what we call a maximum, or in particular, this is a local maximum. It's not a maximum for the function. Well, this is obviously greater. This is a minimum, a local minimum. It's clearly not an absolute minimum for the function because this function will go down infinitely. But these are local max and local mins. And we need a definition for that. So we're going to call these intervals I, I1, I2, and 3, or I'm just going to generically call them an interval. So a local maximum is, again, this is kind of a, I'm going to write the definition, we'll talk it through so it makes sense. Is f of a such that a is a member of the interval, and for all x member of the interval, f of a is greater than or equal to f of x. All right, so I guess I should clarify the terminology. There's the x, which we're calling a, where the maximum exists, and then there's the actual y value, f of a. And we say the maximum, the f of a, the height that this gets to, is some f of a, where a has to be in the interval, and for all other x's in the interval, that f of a is greater than, at that x. So for all x's around the interval, for all x's around this point on the interval, I guess actually the interval we're talking about here is, I should clarify. It's from here to here. That's my eye that I'm talking about. For any x along here, if I find f of x, it's less than or equal to f of a. That's our very mathematical definition of this local maximum. And the local minimum is just f of a. It's the same definition, except at the end. Less than or equal to f of x. That would be local minimum. And again, all that definition seems a little complicated. It gives us something, or if you want to prove that a function is a maximum, local minimum on an interval, we have something to show this, and that's the definition. It's possible for some f of a for all x in the domain, f of a would be greater than or equal to f of x. You could have this. That would be an absolute maximum. In other words, across the whole domain of the function, this is the largest value you can get. Functions don't always have an absolute maximum. Well, this function doesn't have an absolute minimum. You can't find some x where at that x, the function is always its smallest, because you can always go smaller. Now, very important subject in the next class, calculus, is how we find these local maximums and local minimums. In our example here, you can just kind of read it off the graph. But this is an important concept because often you have a function that you want to minimize or maximize for some purpose. So for example, in economics, you might want to maximize your profit, or you might want to minimize your costs. And if you have the function as an algebraic expression, you have methods to find these maximums. Now, at the moment, again, I'm going to mentioned, you have a calculator. If you look at this calc function, you'll see that 3 and 4 on it for the TIs is find a maximum and find a minimum. Find a local maximum or local minimum. The way the TI calculator is going to work, it's not just going to go out. I mean, look, this has 2 maximums. Which one do you want? How's it going to figure it out? You have to give it some help. So you give it a left limit and a right limit. You say, all right, go find the maximum between those 2, and it will do it for you. It'll get you a approximation, which may or may not be the exact value. All right. All right, so any questions? This section is kind of, I don't want to denigrate it, but it's kind of a jumble of ideas that we're going to be using in the future. Any questions about anything we've done so far today, or? All right, so we're gonna once again switch gears. And our next section is going to talk about something called rate of change. Rate of change. So let's think about what that might mean. During the day, maybe it's we've had some hot days, might be 80 degrees Fahrenheit. And, say noon. And then maybe by, let's say midnight. Maybe it's down to, on a hot day, probably doesn't get that cold. So the temperature is cooling, right? So there's a number that represents not the temperature, the rate at which we're cooling. So we have temperature, just use Fahrenheit per unit time. Now, the graph of that, let's say this is noon and it's midnight. It's not the way temperature works, but it could be a straight line. Right? With some slope. And the m in that slope is a rate. But it might not be like this. It might be some kind of complicated thing here. It might go down, might go up a little. It might be complicated. In which case, what we mean by a rate is a little complicated. In a future calculus class, you'll learn something called instantaneous rate. At any point, you can assign some rate value, but we're not going there. So what we're going to be interested in is some number that over the course of this is an approximate rate or an average rate over that period. Let's look at a few, there's some good examples from the book here. They talk about the temperature in the Sahara Desert. In terms of days, where days from 0 is June 1st. And let's say it's 104 plus 1 over 4d. So on the 4th day, it's 105. On the 8th day, it's 106. It's going up for a while, at least through the middle of the summer. Oh, I hadn't thought of this before. It's actually in the Sahara Desert in the middle of the summer. It was a lot hotter than 104, 130. 130 in the shade, because, if you're like next to like a metal box absorbs the heat, and so it's hotter, but, I don't know. So the rate here is what? The rate that is changing is 1/4 degree per day. Again, that's assuming that somehow the temperature just changes in a nice straight line. Here's an example that may get closer to home. It gives you, this is a cost function based on years since 2015. So 2015 is year 0. And this is the supposed cost of a college education in this country. That's the cost if you're paying full tuition. Maybe you're racking up loans. It's on the increase. Every year it goes up $1,000. Again, this is the rate, $1,000 per year. And again, each of these is represented by a function y equals mx plus b, which recognizes a linear function, a function whose rate is the slope, which is m. Now, you might not have a function that looks nice like that. You might have a function where it goes up, even more, maybe levels off, goes down, right? You might have a function where on a particular interval, the rate is constant. Okay? So you have one rate here, another rate here. This is kind of a 0 rate, right? And as I mentioned, it might not be like this at all. It might be just a smooth curve. So in this class, we're going to be interested in dealing with this in a very simplistic manner. And we're going to define something called the average rate of a function. Over some interval. And here's our definition. The average rate of a function from A to B is f of b minus f of a over b minus a. So what are we doing here? Well, in this interval here, we just take the value of the function at the beginning, and the value of the function at the end, find their difference, and divide by the length of the interval. So that's overly simplistic, but that's our definition. So as an example, what is the average rate of some function f of x equal to x minus 3 squared on the interval 1, 3? Well, we just apply the definition, a from 1 to 3 is f of 3 minus f of 1 over 3 minus 1. F of 3 is 0. F of 1 is 1 minus 3, negative 2 squared is 4 over 2, or the average rate is minus 2. That's kind of all there is to it. So the pearl of wisdom here is we have this idea that tells us how a function is changing in a very gross manner, average manner. Again, you can see where knowing this in a little more detail might be more useful, but again, we're not going to learn mechanics in this class. We're just getting the mechanics rate. Calculus class, we're much more interested in rates of change for complicated functions. Here we're just looking at these as if they were very simple functions. Okay, I think that's it for today. I'll hang around